Hi everyone. Now we are going to get into the importance of groundwater. Now that we know what groundwater is, how groundwater moves, we'll talk about why on earth do we care about groundwater. So here we're going to be focusing on the last two of these outcomes to differentiate between different types of wells and springs, and then talk about how groundwater can be depleted or damaged. So why is groundwater important? So, double importance, it's very important to people. A lot of our drinking water, as well as our agriculture and a lot of industry, depends on our groundwater. And then it also has a geological importance, of course. So, we were talking about it in this class. It can be a big erosional agent, so causing a lot of dissolution. And it also contributes to lakes and streams, which form a lot of the geology and the features and landscapes that we see on our surface. So about 30% of all fresh water on Earth is in groundwater, is below the surface of the Earth. 30% of all of our fresh water. So how do we access that? Because as you know, living in California, water can be very scarce. So, how do we access water from our groundwater? One way is through natural springs. So, springs, that is where our water table meets the surface of the earth. So, where our water table meets the surface, or where the water table is above the surface of the earth, we are going to have water seeping out. So, that groundwater is going to seep out to the to the surface, which we call discharge. So this is usually in a valley where we have a dip in the surface. Here we're going to have wetlands. You're going to have a lot of vegetation. You're going to have saturated soils year round. It usually won't freeze, and often you find streams. There's also what we call structural springs. So very similar. It's where the water table meets the surface of the earth. However, it is caused by a geologic structure. So it's caused by the water meeting some sort of impermeable barrier, and then the pressure of that is going to push the water to the surface. So for example, here we have a fault line. So we have a aquifer layer with our water in it. It meets a fault line where it meets a different type of rock. The pressure of this water moving and hitting the fault where it can no longer pass through because it's a different type of rock, the water is going to come to the surface right at that fault line, right where that water meets. So we're going to have a structural spring. So it's a spring here due to the fault line. Something similar here where we have an aquifer layer that is capped on top of this aquitard layer. The water is going to seep out in between the two layers because this water, as it grows, as water percolates, there's going to be a lot of pressure. That water is going to seep out in between the two layers because it can't move any further down because this gray layer is an aquitard where the water cannot move through. So along with springs, which are natural, we also have wells. So wells are where people have dug downwards holes, sometimes pits, to access the groundwater. So to get that groundwater up for human use. So we have ordinary and artesian. So ordinary wells are where a hole is dug into the aquifer, that water seeps up into the hole, seeps up into the well, up to the level of our water table, and then you have a pump, or in the old days, a bucket, where you would pull the water upwards. So here it's literally just digging a hole all the way down into the water table so that the water will seep in and fill up your well. Then you can get the water. That would be an ordinary well. An artesian well is where you have a hole into an aquifer and there's enough pressure that the water rises on its own above the water table. So you don't need to reach down into the water table with your pump or your bucket. The water is actually going to rise up to the surface on its own due to the pressure. So an artesian well might look something like this. where you've dug a hole into your aquifer, there's so much pressure that the water comes up on its own. Here is a map of our groundwater supply on Earth. So this is per capita water consumption. And here we have an insufficient water supply in gray and yellow and orange, and a sufficient water supply in the blue colors. So if you look at this map, you should notice that it's not the same all over the Earth. So we don't have the same amount of groundwater availability over the Earth. If you continue looking, you should notice some patterns. So for example, here we have very low groundwater. This is also a very, very large desert. So here in our desert regions, here as well, here in Australia, we have very low groundwater supply. However, then when you look at our rainier locations on Earth, here's a nice big rainforest. Here we have a lot of rain. We're going to see sufficient water supply. The east coast of the US has much more groundwater than the center or the southern west coast of the US. That Pacific Northwest has quite a bit of groundwater. So where we have more rain, we're going to have more of groundwater supply. Where we have less rain, there's going to be a lot less available groundwater. So that water is very, very, very important to us as people. So fresh water is a huge resource that we absolutely need. But there's two factors that really play a role. Those being quality and quantity. So for our freshwater supply, in terms of human use, we need a certain quantity, but we also need a quality. So quality of water, we need clean drinking water. So it's not that there isn't enough water. It may be just that the water is not actually usable for us as drinking water. So about 1.2 billion people on Earth don't have access to clean drinking water. That is the quality problem with fresh water as a resource for humans. With quality, we can think about groundwater contamination. So contaminating that water beneath the water table in our groundwater aquifer. So this can happen naturally, but it also can definitely happen due to human activities. So agricultural waste, waste from industry, septic tank discharge, landfills. What else do I have listed here? Different chemicals. Oh, mining. So acids from mine waste, just the waste of mining. Fertilizer from farming. All of those chemicals. All of that can infiltrate downwards and get into our water table. It's usually not recognized until the damage has already occurred. So it's not easy to see that the acid waste is entering our water table until we're trying to use that water. And cleaning up the groundwater is incredibly expensive. It takes a very, very, very long time, and it is very difficult. So that really, cleaning up the groundwater is not really a viable option for controlling the contamination. Really, the contamination needs to stop before it starts. And then in addition to the quality of our water, we need a certain quantity. So water moves from place to place. This can cause a lot of environmental issues as well as political issues. For example, when the water crosses a border of a state, crosses a border of a country, whose water is that? An excessive use or overuse of water is going to lower our water tables. Springs and rivers can dry up. We can have subsidence or sinking of the surface of the earth. as well as intrusion of seawater into our water table. So using groundwater, here is a cartoon of two wells. So here we have a shallow well. You'll notice it's not as long as here, which is a deeper well. So wells are going to extract the water. So we've dug down into our water table, and this well is going to be able to pull up water from that water table. However, it's going to use up all of the water right around the well first. So what this does is it causes a little dip, or sometimes it can actually be very large, dip in the water table, which we call a cone of depression. So this cone of depression around the well, as you continue using water around this well, as you continue lowering the water table right along this well, these cones of depression can actually cause wells to dry up. So even though there might be water nearby to either side of that well, the well will use up all the water right in its area, because as time goes on, as you're using more and more water, the dip in this water table is going to get more and more severe, to the point where the water table is lower than the well can reach. So wells can dry up just due to overuse. And then if we continue using groundwater, here we have, let's say this is before, we have a stream where the surface is beneath the water table. Here, right where the surface is right at the water table, we have a swampy area. Here we have a forest that has a very high water table, lots of trees able to thrive. Over many years of water usage, here we have our three wells here pumping water upwards to give water to this new city. That water table is going to lower and lower and lower and lower, to the point where now this riverbed is dry, the swamp has totally dried up, there's much less grass, and these wells are almost run dry. So that water table is lowering to the point where it might actually dip beneath the length of the well. What that means is the wells are going to need to be dug deeper and deeper and deeper as use is continued. So this can change a lot about the groundwater flow. You can change direction. You can totally reverse the flow of groundwater due to overpumping and overuse, and what we call groundwater depletion. Another important thing to think about when we think about groundwater is saltwater intrusion, or saline intrusion. Saline is saltwater. So where we have groundwater near the coast, removing that groundwater can cause what we call saltwater intrusion, which means saltwater is intruding into the aquifer, into the groundwater. So this can poison or ruin all of the fresh water. What happens is, here we have our ocean water, and here we have our fresh water. And here, where they meet, you're going to have some intrusion of ocean water. You're going to have some mixing of this fresh and salty water. Here we have our well, so it's going to be pumping more and more water upwards. So what's going to happen is you're using all of this fresh water. The fresh water is moving towards the well, so you're pumping water that will now want to fill in to the well. What you're doing when you're by the coast is also pulling ocean water in towards the well, into your aquifer, into your groundwater supply. So you're pulling too much water up to the surface, so all of the water in this whole area is going to want to move in towards the well. This is what happens when you're pumping too quickly or too often, too much. You're sort of changing the boundary between the fresh and the salty water. That boundary is going to move, so this whole area is going to move towards the well. So you do not want your well to be pumping up salt water. That would be very much against the entire point of the well. So one way to offset this is to have your well that's pumping up your fresh water and then build a second one, but it's called an injection well. So what you're doing is you're pumping water back down. So you're blocking the intrusion from coming in towards your pumping well. So this well, you're going to have pumping up your fresh water, and then you create an injection well that is on the ocean side. So in between your pumping well and the ocean, you have an injection well. So it creates a barrier that's going to be pumping water back down, allowing your pumping well to continue pumping up fresh water. So you might be thinking, well, what are we pumping down if we need the water? How is there also water to pump down? This is where you might have reclaimed water. So water that has been slightly cleaned. It's been used by humans. It has been slightly cleaned, so it's not necessarily safe to drink, but it's safe to put back into the groundwater, into our water table. So we in Southern California, especially Orange County, do a lot of water reclamation. We reclaim a lot of water, and we do actually pump it down back into the groundwater table. So this can be a really big problem, this saline intrusion, if you don't have that injection well. So if all you're doing is pulling up your fresh water, eventually, here's your well, you're going to reach the point where you have saltwater intrusion. You're going to then be pulling up salt water in your well, and it is absolutely useless. So another thing to consider with pumping groundwater is in between the different sediments. So when you remove that water, the sediments are going to compact down because nothing's left in between. What that means is the ground where we're standing is going to sink downwards as we pull the water up out of it. So this can cause really big damage to roads, to bridges, to anything built on the surface, especially when we're removing water quickly. So when we're using a lot of groundwater too fast or much faster than it can be replaced, which is what we are doing now in California, we're going to see subsidence or sinking of our surface. So here is an image of a man standing with this pole here, and the surface of this ground, so where he would have been standing in 1925, was up here. In 1955, it had subsided or sinked down to here. 1977, it was here. I wish we had an updated version of this because I know this is in Central California. No, excuse me. This is San Joaquin Valley, California. So it has continued sinking. There is still a lot of subsidence. So the surface of the earth is literally sinking downwards as we are removing that groundwater. So a big problem with this is that it's irreversible. So once we pull the water out, that soil is going to compact. The sediment's going to compact together. There's going to be no more porosity. So the pore space is collapsing. So you can't put water back in. So you can't recreate your aquifer because you have destroyed the porosity and the permeability of that rock layer by removing all of the groundwater. So you can't go back years later and try to inject water deep down in the surface because there is no porosity. There's no pore space to be filled with water. So when we pulled that water up in the first place, the sediment compacted, there is no porosity left. So in California, about 70% of all the rivers have been engineered to move water from Northern California to Southern California. So Northern California gets more rain than we do down here. About 70% of rivers actually have been engineered by people and changed so that the water flows to Southern California. So here's a map of all of the aqueducts in California that have been built. Not all of them, but the big ones that have been built to transfer water to Southern California. Where does our water come from? So if you are in Southern Orange County, 100% of your water is imported. So all of the water used in Southern California either comes from the Colorado River or from rivers from Northern California. In Northern Orange County, so that's where I am right now, about 25% is imported from Northern California or from the Colorado River, and about 75% of water comes from groundwater that is recharged by the Santa Ana River, which is not very full most of the year. So Southern Orange County down by Saddleback, 100% of the water that is used is imported. It all comes from somewhere else. It's really, really interesting. So here we have, excuse me, a bit of a outline, little cartoon showing the way that we extract groundwater in Orange County. So Orange County is actually, I believe it was the first county in the country to start injecting water back into the ground. So Orange County, out of necessity, has done a huge amount of work protecting the very little amount of water that we have. So here we have the Pacific Ocean. This is seawater intrusion here in the green. So our production wells are where we're pulling water up. Injection wells are where we are injecting water back into the earth. So this is where we are injecting a lot of that reclaimed water to try and stop this saltwater intrusion. So it's also good to keep our aquifers full. So since we are pulling water up and injecting at the same time, we're not seeing as much of that collapse of the porosity. We're not seeing that collapse of our sediments that we would if we were just pulling up water constantly, emptying our groundwater supply. So the water supply in California, as you might know, the supply does not equal the demand. We are in a very drought-prone region. We use more water than we have. So there's a lot of studying going into where will our water come from in the future? How will we bring water to this area? This is still a rapidly growing area in terms of population. Snow in the mountains is something that is generally very reliable. All spring it will be melting. As temperatures rise, we might see less snow, we might see earlier melt, we might see faster melt, which means we will not have access to as much snow in the mountains to supply our fresh water. So that is something people are definitely thinking about. Groundwater, how secure is our groundwater? How much can we use without causing irreversible damage? And then also importing. So importing water from other places. These are really the three options for our future water supply. And all of them have quite a few unknowns still. So water supply in California is very scarce. Southern California does not have the water to fuel the people and the economy that we have here, so it has to be brought in from somewhere else. Really, there are two options to help us solve the water scarcity issue. One would be decrease the demand, so stop using so much water, conserve water. This is increasingly difficult as population increases. So as population increases, it becomes more and more and more and more difficult to conserve water because there's more people need more water. Another thing would be to increase our supply. So find some new technology that will allow the supply of water to increase. Sounds awesome, but these new technologies, each of them have advantages and disadvantages. So I'll show just a few here in our last few slides. So here we have the Orange County Groundwater Replenishment System. So this is what I was talking about, where we are pumping water back into the groundwater supply here in Orange County. So it treats the human wastewater, so all of the wastewater that we use in these, all of our water, Orange County water, all of the Orange County water districts, excuse me, they treat the used water just enough until it is drinkable again, until it is almost perfectly safe. And then it is pumped back down into the groundwater. So one of the main reasons that this is done is that people were not okay with drinking treated water. So they actually treat the water until you could drink it, but then they pump it down into the groundwater so that when we pump it back up, it doesn't have to be labeled as treated water or treated wastewater, because people were not interested in drinking treated wastewater. So Orange County was a leader in the country in treating water, pumping water back down into the groundwater reserve. This is a really, really great way to conserve water or increase the water supply, is to reuse the water that we have. So instead of just letting it go, letting it flow back into the ocean, actually reusing it. And this does also help keep the groundwater reserve and the groundwater reservoir alive and working. So another option is trying to recycle water. So here is a way to take our water and treat it. So we can use some filtration, we can use reverse osmosis, and then also treat the water with ultraviolet light to try and clean it up. This is water that can then be infiltrated downwards in between that seawater intrusion to decrease seawater intrusion, keep up that barrier, and help recharge the groundwater. So these are the different steps. I'm not going to go into the details of how this works, but this is some of the different steps that we go through to actually clean up our wastewater. If you're interested, I'm happy to talk more about this, but for this lecture, we don't need to go into too much about the different steps that are used. Another option is desalination. So taking seawater, so water directly from the ocean, and treating it to be fresh water and able to be used. So there's a lot that has to go into this. A lot of it is in the treatment. So you're treating, you are completely removing the salt. So then what you'll have left over is fresh water and incredibly salty water. So we call that brine. So the wastewater of desalination is called brine. That would be all of the salt in the water in about 1% of the water. So it'd be incredibly, incredibly, incredibly salty and completely separated from the fresh water, which the fresh water could then potentially go into storage and be ready for using and drinking. So there is a desal plant in Carlsbad that was built relatively recently. It started production in 2015, and there's another one that is being built right now in Huntington. So it is supposed to begin production of water in 2022. So it's being built in Huntington Beach, right on the beach. So this may be a really good option for those towns that don't have much water but are right on the ocean. There's quite a bit that goes into this, so it can be very expensive. It's very it consumes a lot of energy, and you have to be careful with that wastewater. So that brine that I was talking about, it's great to clean up the salt, to create fresh water from our salt water, but then what do you do with all of the salt? So these plants usually take a very long time to get approved and to get started because there's so much that goes into creating a desalination plant. And then there are some other options that we don't necessarily use here in Orange County, but there are some places that actually capture water from the air. So for us in Orange County, that wouldn't work because we don't have very much water in our air. But in a place that has a lot of fog, you can, there are some systems that will capture that fog, turn it into liquid water, and then capture that liquid water for use. So here is a cartoon of that cone of depression. So here are two guys with their well. They're trying to get their groundwater, but they've used too much. The well needs to be deeper. They've used up all the water here. And he says, well, where did our groundwater go?